Have you ever wondered what would happen if you approached a black hole? Well, today we're going to delve into that very mystery. You see, black holes aren't your regular celestial bodies. They're incredibly dense objects in space, so dense that their gravitational pull is stronger than anything else we know. Imagine an object so heavy and compact that nothing, not even light, can escape its gravitational force. That's what we're dealing with when we talk about black holes. But there's more to these cosmic leviathans than just their gravitational pull. There's a fascinating, albeit mind-boggling concept at play here: time dilation. Now, you may have heard this term in science fiction movies or read about it in books, but it's not just a speculative concept. It's a real, scientifically observed phenomenon. Time dilation is intrinsically linked to gravity. It's a concept that comes straight from Einstein's theory of relativity. In simple terms, it suggests that the stronger the gravitational force, the slower time passes. This might sound a little abstract, so let's put it into perspective. If you were to observe a clock near a black hole, that clock would appear to tick slower than your own. The closer the clock gets to the black hole, the slower it appears to tick. This isn't because the clock is malfunctioning, but because time itself is being stretched out by the black hole's immense gravitational pull. That's right, black holes have the power to stretch time. This doesn't just affect clocks, but everything and everyone that comes near them. Yes, even you, the daring space explorer, would experience this time dilation if you approached a black hole. But what does this mean for you? Well, the effects of time dilation can be quite severe, as we'll explore in the next scene. So far, so good. But what does this mean for you, the daring space explorer? You might ask. Well, hold on to your space helmet, because we're about to delve deeper into the mystery of black holes and the secrets they hold about time, space, and our existence. Ever heard of time dilation and scratched your head? It's simpler than you think. Let's start by imagining time as a river flowing at a steady pace. Now, picture a clock submerged in this river. The stronger the current, which we can compare to gravity, the slower the clock ticks. That's essentially what time dilation is all about. Now let's take this a step further with a practical example. Consider two clocks, one at sea level and another on top of a mountain. Now, gravity is stronger at sea level because it's closer to the center of Earth. Hence, the clock at sea level is in a stronger current and will tick slower than the one on the mountain where the current is weaker. This difference is minuscule, but it's there. This is a real phenomenon proven by extremely precise atomic clocks. These clocks were placed at different altitudes, and indeed, the one closer to Earth's center ran slightly slower. This is time dilation in action. It's a fundamental part of Einstein's theory of general relativity, which tells us that gravity is not just a force pulling objects, but it's actually the warping of space-time by mass and energy. You might be wondering, why does this matter to me? Well, the effects of time dilation become much more pronounced near enormously massive and dense objects such as black holes. Imagine the river of time near a black hole. The gravity is so intense that the current is immensely strong, causing time to crawl. We can't observe this directly because, let's face it, none of us are packing for a trip to a black hole anytime soon. But we can study the effects of time dilation through various experiments and observations right here on Earth and in our solar system. In a nutshell, the stronger the gravity, the slower time passes. Keep this in mind as we dive deeper into black holes. Now, what does this time dilation business have to do with black holes, you might ask? Well, it's quite the fascinating phenomenon. You see, our understanding of time dilation becomes extreme when we consider black holes. These celestial objects possess gravity so intense that it warps the fabric of both space and time. Imagine a heavy ball sitting on a stretched-out sheet, causing the fabric to sag. That's how a black hole distorts the space-time around it, only on an infinitely larger scale. Now, according to Einstein's theory of relativity, the stronger the gravitational field, the slower time passes. This is why, near a black hole, where gravity is extremely powerful, time slows down significantly. This is time dilation in its most extreme form. Now, let's imagine you're a brave space explorer, venturing close to a black hole. As you approach, your clock would tick slower compared to a friend who's watching from a safe distance away. From your perspective, time would seem to pass normally. But for your friend observing from afar, it would seem as if your time is slowing down. As you get closer and closer to the event horizon, that's the point of no return for a black hole. Your time would appear to slow down more and more from your friend's perspective. Ultimately, as you reach the event horizon, your friend would see your time come to a complete stop. You would appear frozen in place at the edge of the black hole. Of course, you wouldn't notice any change. To you, time would still seem to flow normally. But for your friend, and indeed for the rest of the universe, you would appear to be frozen in time indefinitely at the edge of the black hole. This is the bizarre and mind-bending reality of time dilation near black holes. A reality where time can stretch and squeeze, where seconds can become hours, and where a moment can last an eternity. Imagine being frozen in time from an outsider's perspective as you approach a black hole. Fascinating, isn't it? Sounds thrilling, right? But should you, a daring space explorer, approach a black hole? Well, let's talk about that. You see, black holes are not exactly the friendliest of cosmic phenomena. Picture this. You're being stretched into a long, thin strand like a piece of spaghetti. This horrific scenario is known as spaghettification, and it's what would happen if you got too close to a black hole. The gravitational pull is so extreme that it stretches anything that comes near into a thin, elongated piece of matter. So unless you have an unusual fondness for pasta, this is a situation best avoided. But the perils of black holes don't end with spaghettification. Let's not forget about time dilation. Remember, time and space are interconnected. The stronger the gravitational field, the slower time passes. This is a fundamental principle of Einstein's theory of relativity, and black holes, with their intense gravity, take this principle to the extreme. Imagine you're orbiting a black hole. For you, only a few years might pass, but back on Earth, centuries could have gone by. Your return would be a massive time jump into the future. You'd find an Earth that has moved on without you, an Earth that is potentially unrecognizable. Your friends, your family, your favorite coffee shop, all could be gone. You'd essentially be isolated in time, a relic from the past. It's a sobering thought, isn't it? So while the mystery and allure of black holes may be enticing, the reality is far from glamorous. They're not just dangerous, they're potentially isolating, transforming a simple journey into an irreversible leap forward in time. Remember, space is vast and filled with wonders to explore. But some things are better appreciated from a distance. So while black holes are fascinating to study, they're not ideal vacation spots. Not unless you fancy a one-way trip into the future. Black holes and time dilation. Fascinating and mind-boggling, aren't they? We've journeyed through the galactic mysteries of black holes and the enigmatic concept of time dilation. Let's take a moment to revisit some of these key points. Black holes, these cosmic conundrums, are regions in space where gravity is so strong that nothing, not even light, can escape. They're like the universe's ultimate trapdoor. Once you're in, there's no coming back. Then we delved into time dilation, didn't we? A concept that, quite frankly, sounds like it's straight out of a science fiction novel. Yet, it's a fundamental aspect of our reality. Time dilation is the difference in elapsed time as measured by two observers due to a relative velocity between them or due to a difference in gravitational potential. When these two concepts collide, black holes and time dilation, we stumble upon an even more astounding phenomenon. As you approach a black hole, time would seem to slow down for you relative to someone observing from a safe distance. The closer you get, the slower time appears to pass. But why should you never approach a black hole? Well, aside from the obvious fact that you'd be stretched into a thin strand of atoms, a process charmingly known as spaghettification, the time dilation effect would mean you'd never be able to communicate with the outside universe again. It's a one-way trip into the unknown. Yet despite their dangers, black holes and time dilation are undeniably captivating. They challenge our understanding of the universe and force us to look beyond our everyday experiences. I encourage you all to continue exploring these incredible phenomena. There's so much more to learn, so many more mysteries to unravel. Remember, space exploration is about curiosity and the pursuit of knowledge. But when it comes to black holes, it's best to admire from a distance.